preceding two lectures. So in the first lecture, I've defined the notion of symmetries that we're using. I've defined the notion of anomalies, and we discussed it in much more detail in the tutorial sessions about the singular and non-singular part of the free energy and why anomalies have to match and why anomalies are related to the singular part of the free energy. Genuine anomalies are related to the singular part of the free energy and so on. And then we started discussing the particle in a circle model, which is a good pedagogical example just so that I don't have to derive various facts about Yangmills theory. I'll just state them and hope that the analogy will be compelling enough that you would believe what I'm saying. And then we discussed the symmetries of pure U1 gauge theory, 3 + 1 dimensions, the existence of an electric one-form symmetry and a magnetic one-form symmetry, associated to the world lines of probe external monopoles and probe external charge particles. And then I started discussing SUN gauge theory, whose action is reviewed here. And I have emphasized that there is a theta parameter, much like the particle in the circle model, which is 2 pi periodic. And furthermore, the fact that the physics of Yangmills theory is 2 pi periodic is achieved in a similar fashion to the particle on the ring model, where there is a similarity transformation by a well-defined unitary single-valued operator given by the exponential of the ChernSimons action. That's the operator that performs the similarity transformation. And I'll talk much more about ChernSimons actions soon. But for now, I'm just stating it. And then we also discussed the consequences of anomalies that could be either to symmetry breaking, degenerate ground states, topological field theories, gapless theories, and these are not mutually exclusive. There could be several things happening at once. For instance, if there is a continuous symmetry breaking, then you'd also have a gapless mode, and not just a degenerate vacuum. Are there any questions before we begin the discussion of anomalies in SUN gauge theory? Any questions that are left from the tutorial session or the main lectures? Okay, so I'll jump right in. So the main first claim about the pure glue, this is just the pure glue, pure Yangmills theory, was that that there is a Zn electric one-form symmetry, Zn electric one-form symmetry, which acts on the external probe particles, which are in representations that are not divisible by n. So yesterday, also in the tutorial session, we've discussed the possible representations of probe particles. So you could imagine, since the theory doesn't have dynamical charge particles, you could imagine that you add to the theory some very heavy, infinitely heavy, essentially, particle in some representation R of SUN. It could be an irreducible representation. And we discussed the fact that if you draw the world line of such an infinitely heavy probe particle, there will be some back reaction of this line on the surrounding Yangmills fields. And you could solve that problem classically, just to find the field configuration due to some probe particle. And then the question is there a generalization of the Gauss law? Can you, by doing measurements at infinity, detect the representation of the probe particle? So in U1 gauge theory, of course, you know from school that the Gauss law works and you can detect the charge of the probe particle by measuring the total flux of the electric field, but that's nothing but the statement that there is a U1 one-form symmetry. That's the highbrow way of saying that the Gauss law works. In SUN Yangmills theory, because the theory is nonlinear, and you get confused, because if you measure the flux, since the gluons carry quantum numbers under the Yangmills field, you get confused. So essentially, this information is polluted by the nonlinear structure of the Yangmills equations, or more precisely, the fact that the gluons themselves carry charge under the SUN gauge symmetry. So what can you measure? So in terms of the Yang tableaus, this representation has some boxes. So what you can measure is the number of boxes, mod n. Okay, and that's the physical origin of this Zn symmetry. So this Zn symmetry is really a discrete version of Gauss's law. So it's not that Gauss's law completely disappears in SUN gauge theory. There is a discrete version of the Gauss law. And the number of boxes mod n is all you can measure, because every two representations with the same number of boxes mod n can be eventually connected by tensoring with the adjoint representation. So this is the physical meaning of the ZN symmetry. So this is fact number one that we explained in the previous session. Fact number two that we explained is the existence of a time reversal symmetry, or alternatively CP symmetry. It's the same thing due to the CPT theorem. And as in the particle on the ring model, such a symmetry exists at two values of the theta parameter, namely 0 and pi. This symmetry exists for all theta, but this symmetry exists only at 0 and pi. So the main claim, which I'm not proving, but I'm alluding to an analogy, that's why I discussed in detail the particle on the ring model. So I'm alluding to an analogy. The claim is that there is an anomaly in the sense of a 't Hooft, not in the sense that the symmetries are misidentified. There is a physical anomaly which involves time reversal symmetry and the ZN electric symmetry. So this anomaly involves both symmetries. I'm not going to write down this anomaly for you, or am I going to write any concrete formulas?
So
but
until now everything was classical?
No, these are statements that are true in the full quantum theory. They're also true classically, but they're also true, well, classically the theta parameter has no significance. So some statements here are a little void of content classically, such as the symmetry at theta equals pi. But these are true statements about the full quantum theory. There is a true ZN one-form symmetry in the full quantum theory, and there is a true time reversal symmetry at both theta equals 0 and theta equals pi. The non-trivial statement is that there is an anomaly that involves this one-form symmetry and this ordinary zero-form symmetry, which is a space-time symmetry. You can think about it as either a time reversal symmetry or a CP symmetry. Okay, so I'm not going to try to write this anomaly precisely, but I'm going to give you a hint of why this is good. I'll give you some interesting applications of this anomaly for the phase diagram of Yangmills theory, which is a decades-old problem. And then I'll show you that a similar anomaly exists in other models, and it also leads to interesting corollaries. Are there any questions before we begin?
So no fermions.
Just pure Yangmills theory.
Just pure Yangmills.
We'll discuss a model with an adjoint fermion for a couple of minutes when I finish with pure Yangmills theory. Yes?
How do you know you're able to quantize the theory in a way that has these symmetries?
That's an excellent question. So for instance, lattice people will have an extremely hard time to quantize the theory at theta equals pi. There is a lot of recent work on that. In fact, some that I view as extremely promising, but it's still not something that they have done. Well, I don't believe there is an extremely good answer. We just believe that those theories exist. I mean, we know that they're asymptotically free and they seem fine. These are like our most canonical quantum field theories in some way. I mean, we believe that nature is described by SU3 gauge theory with some quarks. So removing the quarks by giving them a mass should not cause too many troubles. Nobody has proven that these quantum field theories exist. In fact, the first thing that you have to do to get the Clay prize is to prove that these theories exist, and then prove that they have a mass gap. So, but you have to first prove that they exist. It's not something that we've done.
The problem is how to have a theta equals pi.
And even at theta equals 0, it's not been proven to exist. That's the first problem in the Clay prize. You have to first prove that it exists, and then prove that it has a mass gap at theta equals 0.
No, but theta equals 0 is fine, right? Pure glue theory.
Well, I'm just saying that this is the first thing you have to do to get the Clay prize, to prove that it exists. Well, we have extremely good physical arguments that these theories exist because they're asymptotically free, and then you imagine doing a spin block transformation, and there should be a good infrared limit. But, you know, there is some distance between that and the mathematical proof. It does obey everything that physicists like a theory to obey. So, any other questions? Yes? Yes? No, this is a. It's on the same status as the anomaly in the particle on a ring model. It's an anomaly of the full quantum theory. I think we've discussed that already. So what people sometimes call an anomaly in textbooks is when you have a misidentified symmetry. It's something unphysical. It's like you thought that there is some symmetry, but then it doesn't exist. Okay, so what do you do with that? It doesn't teach you anything. It's just that the symmetry doesn't exist. Here, both of these symmetries exist, and they act linearly on the Hilbert space. If you quantize the theory in a big torus, they act linearly on the Hilbert space in unitary representations. They actually exist, and they lead to word identities. But the anomaly is something more sophisticated. It's yeah. So sometimes people distinguish it. They call it a 't Hooft anomaly. So sometimes, when the symmetry is just misidentified, this you would maybe you would call it an ABJ anomaly. Sometimes people use the terminology. A 't Hooft anomaly is something much more sophisticated that has to do with symmetries that actually exist and act on the Hilbert space. But there is some kind of obstruction to gauging those symmetries. But they exist. There is an obstruction to gauging them, but they exist before you try to gauge them. So it's a more sophisticated notion that we've discussed like for an hour yesterday in the tutorial session. It just teaches you something about the singular part of the partition function if you try to couple the theory to background fields. But it's a physical thing. It's not an artifact. It's not an artifact of some. Okay? It's a physical observable. Any other questions? Okay. So, well, what this anomaly means, what is the consequence of this anomaly? I'm going to swipe some technical things under the rug, so the experts in the audience would easily spot them, but I want to just cut to the chase. The consequence of this anomaly, this anomaly exists only at theta equals pi, much like the particle on the ring model. At theta equals 0, there is no anomaly. So the consequence of this anomaly at theta equals pi is that the model cannot be trivial in the infrared. It cannot be trivial in the infrared at theta equals pi. So it's like the opposite of what we expect at theta equals 0, which is that the model is expected by and large to be trivial in the infrared. But at theta equals pi, it cannot be trivial in the infrared. You can say it with full certainty. It's not a conjecture. But what could it do? There are several options. It could be that the model is gapless. So it could really be true that theta equals pi, Yangmills theory is gapless for some values of n, where n is the rank of the group. However, this could be true. Let's say for n equals 2, for SU2 gauge theory, it could well be true. It does not contradict anything we know, and no lattice simulation has contradicted it. It could be true for small values of n, maybe 2. However, for large enough n, we know that this is not the case. So this option is ruled out for large enough finite n. It's hard to say what exactly is this value of n from which it starts being true. But for large enough finite n, it's definitely not gapless. Now, another option is that there is a topological field theory. There could be a topological field theory. And the final option, which is the most compelling option, is that time reversal symmetry is spontaneously broken. So CP symmetry is spontaneously broken. And therefore, there will be two ground states, which are exactly degenerate. But the physics in each ground state is not time reversal invariant. Time reversal invariance is spontaneously broken, so the physics of each ground state is not. You cannot assign the globals well-defined time reversal quantum numbers. But there are two ground states which are related by time reversal symmetry. So this option is the most compelling one because with some mild assumptions, you can prove that it's true at large n. So we're going to favor this option since we can prove that at large enough n it's true, that there are in fact two ground states at theta equals pi. This option of having a topological quantum field theory could be a deconfined phase. So this could be, for instance, a deconfined phase. But we're just going to assume that confinement persists even at theta equals pi, and therefore rule out this option and favor this option. The physical arguments behind this logic is that confinement is something of order n squared. It has to do with the dynamics of pure glue in the large n limit, while the effects of the theta parameter are down by a factor of n. Because the theta parameter is not proportional to n, it's of order 1. And therefore, at large enough n, the effects of the theta parameter cannot destroy confinement. So this more or less this favors the option of a deconfined phase. But for small enough n, any of these options could be true. We don't know. Yeah. Oh, you're asking how would the lattice person detect such a thing? Yes. So in principle, the way lattice people detect symmetry breaking. You could ask the same question about the Ising model in 2 dimensions, which has 2 states in the ferromagnetic phase. The way they compute the free energy, and then there is a correction to the free energy which is not extensive, which is logarithm of the number of ground states. So the structure of the free energy of the Ising model could be something which is like the free energy density in each of these vacua, and then there is plus log 2. And this 2 is the degeneracy of the ground state. So you have to fish after a non-extensive contribution to the partition function. That's option number 1. Option number 2 is you can arrange boundary conditions so that the spins are up on one side and down on the other side, and then the system creates a domain wall with a finite tension. So having a domain wall with a finite tension is another telltale signature for symmetry breaking. So you could do the same here in principle. You could either arrange for a domain wall, which we'll discuss, or you could try to fish out some subleading contribution to the partition function on the big space. Yes?
So how did you use the anomaly to exclude the gap phase or what?
The anomaly rigorously excludes a trivial non-degenerate gapped phase. So it's actually, it's something non-perturbatively correct about Yangmills theory that you can say for any n. And it's up to a matter of guessing, in some sense, what's the correct infrared physics. I'm going to assume that this is the correct answer, and it's definitely true for large enough n, modulo small assumptions. Now, but there could be more exotic phases at small n, and in particular, there has been quite a bit of work recently by both condensed matter physicists and high energy physicists looking at variants of this model at small n and claiming more exotic phases.
But the statements sound very similar to two-dimensional sigma model, O3 sigma model that theta equals pi.
It's extremely similar. It's also mathematically very analogous, and it's more than that. You can even argue that SUN gauge theory in a small torus is in the same universality class as far as the anomalies are concerned. There are papers about it by Yonekura, for instance, and Yamazaki, showing that the anomaly polynomial here is reduced on a small torus to the anomaly polynomial of the O3 model at theta equals pi. Yes?
But there's a difference if one is gapless and the other is not.
Right. At n equals 2, yeah, but at higher n, they are both gapped, presumably. Yeah. Can you just say the second option? You mean, oh, you're asking why did I conclude that this is broken rather than this? The breaking of do you remember what we said about the breaking of one-four symmetry? One-four symmetry is broken when there is deconfinement, okay? So deconfinement is this option. That's when you have spontaneous breaking of the one-form symmetry. Now, why did I say that this is disfavored? I said that this is disfavored because there is a large n argument, which is that the free energy in the gluons is of order n squared, and the contribution of theta is subleading. So adding theta is not going to change the fact that the free energy is something. Now, this argument, we know that the theory, so the assumptions in this argument are that the theta equals 0 model is confined. So Zn is unbroken at theta equals 0. And the second assumption in this argument is that large n works. So if you assume that the model is confined at theta equals 0, and large n works as 't Hooft taught us, then this follows that you can rule out this option for sufficiently large n. So these are the two assumptions here.
Yeah. Well, if you make these two assumptions, you don't really need the anomaly because you know
Yes.
the vacuum energy is theta squared.
Right.
So there must be the
Right.
theta equals pi.
Yes. You can derive it at large n. This is what Nari is saying. You can derive that this is correct at large n. That what the anomaly tells you is that this is true even at finite n. One of those is true even at finite n. And there is an open question of at what small n this may break down, if at all. Yeah.
Can you see what parameters you're using? You said that it can't be non-degenerate, gapless, and
So what's the question? Can you?
what's this statement? How do you know that?
Well, yesterday in the tutorial session, I gave an argument that if a theory has an anomaly, the free energy density has to have a singular piece. A singular piece is a function of sources which are at zero momentum, or very small momentum to be precise. And when your free energy has a singular piece for sources at small momentum, that means that the infrared physics cannot be completely trivial. Now, this non-trivial nature of the theory could be due to gapless modes, several ground states, or even due to a topological field theory. Any of those could produce a singular piece. So you cannot a priori decide which is the correct answer, but you know that it cannot be a trivial ground state. It's just like technically much easier that some Hamiltonian is not trivial than proving that it's trivial. It's much, much easier to prove that a Hamiltonian cannot be trivial.
And we don't know those are the only 3 ways to get something.
These are the only 3 ways I'm aware of. Okay, so I'll proceed now. So we can try to start drawing the phase diagram of the model at 0 temperature. So we take the temperature to be 0 and draw the phase diagram of the model as a function of theta. Theta ranges from 0 to 2 pi without loss of generality. Okay, so so there is one ground state at theta equals 0, one trivial non-degenerate ground state at theta equals 0. This is the whole premise of confinement, a confinement and trivial ground state, for the ordinary theta equals 0 model, and it's supported by thousands of lattice simulations. So here there is one ground state, but at theta equals pi, as we assumed, there are 2 ground states. And since the system is periodic, by the time that you get to 2 pi, there is again one ground state. So how is it gonna look at generic theta? So the idea is that at generic theta, there is a state that comes down, and then this state becomes degenerate, and then this state goes up, the other one goes up, and then it's like that. So this is the picture. This is a standard first order phase transition. Okay, so there is a phase transition at theta equals pi. There are exactly 2 degenerate ground states in Yangmills theory, and this is definitely true at large enough n. So, and then what happens when you heat up the temperature? For reasons that I'm not going to explain, this anomaly still exists at finite temperature. I'm not going to explain why. It would take me too much time. It's not characteristic of all the anomalies. Many anomalies disappear at finite temperature, and you have a trivial gapped phase at finite temperature. But for this one, this is not the case. So for this anomaly can be used even at finite temperatures. So this is different from the ordinary quantum critical graphs that you would, quantum phase transitions that appear in condensed matter physics. In condensed matter physics, the typical picture is that as a function of the temperature, there might be an interesting gapless phase, but as you heat it up, it disappears.
Zohar, I thought the anomaly exists is just some statement about contact terms or something, right? I mean,
No, but it typically disappears at finite temperature.
What do you mean by that? I mean, it's just some property.
Well, the typical system, like a typical, if you look at the literature on, let's say, SPT phases or quantum phase transitions, there could be an anomaly at 0 temperature. You heat it up, it disappears. This is the typical picture. The anomaly does not survive circle compactifications typically.
Oh, sorry, you mean if you take it literally, you shrink the
No,
circle?
finite circle. You take the temperature to be finite, but you look at the physics at distances much below the temperature scale. That physics is trivial typically. In fact, you expect that most models will be trivial at high enough temperature.
Yeah.
Yeah. So this anomaly is of a different nature mathematically. It survives the finite temperature compactification. It survives the compactification on the circle. This is not. This is by far not the usual thing.
I mean, I just thought the anomalies of a quantum field theory or the anomalies of a quantum field theory. It doesn't matter what background you put it on.
It's true, but if you try to understand the physics at long distances below the temperature scale,
It might be hard to see the anomaly.
no, it's not hard to see. It does not appear. It does not affect the ground state. It might affect conductivities or some other things, but it does not affect the physics of the ground state. The technical reason is that if you take the anomaly polynomial, let's say, and you compactify it on a circle, If you don't turn any chemical potentials along the circle, this is just 0. If you don't couple the theory to sources, which have a non-trivial profile on the terminal circle, this just goes to 0.
Okay, that's fine. So you're restricting the sources.
I'm just taking finite temperature,
Okay.
no chemical potentials.
So you're saying no sources that vary over the circle.
Yeah, that are non-trivial on the circle. So typical anomalies don't have any implications for finite temperature physics because of this fact.
Sure.
They have some implications, but they're higher order. They might affect subdiffusion coefficients or transport coefficients, like the Son-Surovka example. But they don't affect the ground state. This anomaly is of a different kind. This anomaly survives the circle compactification even without turning on any chemical potentials. So that's why it leads to somewhat striking conclusions, because we can use it even at finite temperature. Okay, so one phase transition that's famous in Yangmills theory is the deconfinement transition. So while the theory confines at low temperatures, it deconfines at high temperatures. So here, Zn symmetry is preserved. Preserved meaning that the theory is confined. But then at 0 theta, at finite temperature, there is a phase transition where the Zn one-form symmetry is spontaneously broken. This is the standard confinement-deconfinement transition, where Wilson loops, where it takes finite energy to introduce a probe quark into the system, while here it takes infinite energy to introduce a probe quark because of the flux tube. So above this point, the flux tube sort of melts, and it takes only finite energy to introduce a probe quark. So this is a famous phase transition. It's typically first order. So there is a first order line that comes out of here. And since at large enough n it's not going to depend on theta too much, there is some kind of theta dependence, but it's not going to be very significant. So there is a first order line that divides the low temperature phase from the high temperature phase. And we know that from lattice simulations. Below, the Zn symmetry is preserved, but above, the Zn symmetry is broken.
So for each series, is it? It's just for S?
Pure Yangmills, yes, SUN.
Pure Yangmills.
Right.
Then what fermions for S3 you take SU3 with fermions?
I might discuss it soon. I just wanted to start from the simplest example.
So here there is clear statement that it's first order phase transition.
For large enough n.
For large enough, n equals 3 is first order?
Yes, n equals 3 is already first order, but for n equals 2, it happens to be second order. Yeah, for n equals 3, this is already known from lattice simulations to be a first order transition.
So with fermions, people do not think that it's...
He's not doing fermions.
But I'm doing pure Yangmills now.
Okay. I forgot.
Yeah, so for theta equals pi, there is a similar first order transition that comes out of this point. On this point, time reversal symmetry is spontaneously broken. So it's interesting to ask, how do these phase transitions talk to each other? Like, you expect that at high enough temperatures, time reversal symmetry would be restored, because we do expect that in physical systems, ordinary symmetries are restored at high enough temperatures. Like, if you have ever done a calculation of the Coleman-Weinberg potential at finite temperature, if you have such a thing at 0 temperature, the Coleman-Weinberg potential gives you a huge contribution to the mass. So restoring the symmetry at 0. So there are 3 options. One is that time reversal symmetry is restored before the deconfinement transition. Another option is that it's restored exactly at the deconfinement transition. And the last option is that it's restored above the deconfinement transition. These are the 3 simplest options you could imagine. So here there is a very fun application of anomalies that you could actually say which one is right. So let's call the temperature at which time reversal symmetry is restored by TCP. And let's call the deconfinement temperature T deconfinement at theta equals pi. So this is the deconfinement transition temperature at theta equals pi. So you want to know whether this is true or any of the other options, right? This, or this. Which of these options is true? Now, what does the anomaly teach us? Loosely speaking, the anomaly teaches us that there cannot be a phase where both time reversal symmetry and the Zn electric symmetry are unbroken and trivial, right? So we're good here because the Zn symmetry is unbroken, but time reversal symmetry is broken. But if this was the case, we would be in a contradiction with the anomaly, because above this line, there is no yet you haven't yet reached the deconfinement transition. So the one form symmetry is preserved, and similarly, you've already restored time reversal symmetry. So this is actually ruled out. it must be either exactly at the deconfinement transition or above. So the anomaly teaches you that the CP symmetry cannot be restored before you've reached the deconfinement transition. So this is a fun inequality about the phase diagram that you can get just from anomalies. Now, if you look at ADS constructions of this, you can look at ADS, the ADS mock models of Yangmills theory, such as the scenario of Witten, where he has non-extremal D4 branes. In ADS, it happens to be true that the CP and the confinement temperatures coincide. So it's consistent with the anomaly. And there is a question of whether that's always true at large n, for instance. It's hard to settle this question at the moment. But it could be that at infinite n, this is perhaps guaranteed. And at finite n, you would get a strict inequality. So there is still an open question of why is that true at infinite n? Is that a universal thing, or is that just an artifact of the Witten model or other holographic models like Sakai-Sugimoto?
If one would add massive fermions in the fundamental...
Yeah, so now I'll discuss adjoint fermions. I'll tell you what happens for adjoint fermions. There is a little bit of lattice data about adjoint fermions.
But fundamental, what happens if...
Fundamental, I wanted to discuss at the end. I can also give you the phase diagram for the fundamental case at 0 temperature, and there are many interesting phases, but I just wanted to start from the simplest case. Are there any questions about this inequality? And why does it follow from the anomaly? Yeah. Okay. So let me now make a similar claim about the phase diagram of a closely related model. So a similar claim can be made about a closely related model, which is SUN gauge theory coupled to a massless adjoint fermions. A massless adjoint fermion, wild fermion in the adjoint representation. Okay? So if you take this fermion to be massless, this is also known as super Yang-Mills theory. And this has n equals 1 supersymmetry in 4 dimensions, in 3 plus 1 dimensions. So I wanted just to quickly make a similar claim about this model and then switch to the next subject, which is ChernSimons theories and domain walls. So for this model, the story is quite similar. This model has a Zn zero form symmetry, which is just an axial symmetry. And in addition, for the same reason as before, it has a Zn electric one form symmetry. This is just an axial symmetry that I'm not going to explain too much. I just wanted to quote the facts, show you the answer, and then we can discuss it more. So this model does not have a theta parameter, but it has still a phase diagram as a function of the temperature. And there is a similar question about this model, because there are two symmetries, a Zn zero form symmetry and a Zn electric one form symmetry. So at low temperatures, it's known from supersymmetry that the Zn zero form symmetry is spontaneously broken, but the Zn one form symmetry is preserved. This is known from supersymmetry. Then there is a phase transition, which is a deconfinement phase transition. There is a certain temperature above which the theory deconfines and the one form symmetry is broken. And there is then another temperature at which the chiral symmetry gets restored. The chiral symmetry is the Zn zero form symmetry. And at high enough temperatures, you would expect that the symmetry is restored. More generally, we expect that in any normal quantum field theory, all the ordinary symmetries are restored at high temperatures. So the question is, which transition happens first? And using exactly the same ideas as here, you can prove using anomalies that the chiral symmetry cannot be restored before the deconfinement transition takes place. And in fact, this was checked on the lattice in cases such as n equals 3 and n equals 2. And it works. And the inequality is strict. In the cases that were, if you trust the lattice results, there is a strict inequality, not an equal sign. So indeed, the order of the transitions is as here. Yeah, the true symmetry is Z to n, but a Z2 inside Z to n is kind of spin. It's a fermion number. I can write Z to n. People often write Z to n if you want. But then it's broken to Z2. I'll have to change this cross to broken to Z2. Yeah. So lattice agrees, and yeah, so it's a fun example where anomalies lead to constraints on the thermal phase diagram. And in the condensed matter language, this is somewhat weird, this whole thing, because these are systems at which, even at high temperatures, they're ordered. So these systems cannot be disordered, even by thermal fluctuations. As you know, in condensed matter physics, people are interested in anomalies because when you have an anomaly, the system cannot be disordered, at least not by symmetric perturbations. But it can be typically disordered by thermal perturbations. That's why when you raise the temperature, these quantum phase transitions go away. So this class of examples is interesting because they cannot be disordered even by thermal fluctuations, not just quantum fluctuations. Okay.
Now, Weinberg in '74 was claiming he identified a case where actually the symmetry is broken as you increase the temperature. Can you put this in this framework?
Can you remind me what you have in mind?
It was some mineral for which it happens. I don't remember the mineral. Have to look at Google.
As far as I know, Landau-Ginzburg models always restore all the symmetries at high temperatures. So nothing comes to mind. I don't know of a Landau-Ginzburg model that has a broken symmetry at high temperatures. Yeah, so there is a question of why is this theory ordered at high enough temperatures? And it's a hard question. So it seems that zero form symmetries behave more or less as you physically expect, that as you raise the temperature, they must always be restored. And it's hard to construct a counterexample for that. I mean, I know of counterexamples maybe with free fields, but not really physical systems. But it seems that one-form symmetries generally behave in the opposite fashion, that they can lead to non-trivial order even at high temperatures. In fact, that's what they typically do. So instead of thinking about thermal physics, a perhaps more constructive way of thinking about it is to compactify the theory in a circle. So you just study normal Hamiltonian physics, but instead of on R3, you study Hamiltonian physics on S1 times R2. That's perhaps more conceptually clear, because now we're not discussing thermal physics. We're just discussing normal Hamiltonians on a cylinder. So what you expect physically is that when the circle shrinks, all the normal symmetries that are associated to local order parameters must be restored. However, the one-form symmetry is associated to a non-local order parameter. It's a Wilson line. And so from the point of view of the R2, that's a local order parameter because it can wrap the circle. But in the full theory, it's a non-local order parameter. And it seems that those order parameters from the point of view of the R2 can behave in a non-standard fashion. So there could be multiple vacua, even on a very small circle, associated to the spontaneous breaking of that order, of that symmetry. So yeah, if you can recast this discussion in terms of a cylinder compactification, it looks indeed quite confusing. Because typically the small circle limit is supposed to be trivial with one ground state. Because it's kind of analogous to high temperatures. Yes? No. Okay. Any?
It's perhaps more intuitive if you remember that the spontaneous breaking of zero form symmetry is associated with condensation or some operator or something. And if you heat it up, the condensation stops. And with one form symmetry, the condensation of magnetic monopole.
Right.
And the deconfinement transition is just as the intuition says, the condensation stops. So in that sense, it's very much like the thing that is reversed is what you call symmetry breaking. For high form symmetry, it's backward. But it's not, the counterintuitive thing is not between order and temperature. This is actually works exactly as expected. You lose the condensation at high temperature.
Right. So the counterintuitive thing is about the number of vacua on a small circle. So if you look at the limit of small circles of Yangmills theory, there are n vacua. But typically systems on small circles have just one vacuum. So, okay, so I think we hashed this enough, unless there are any more questions about these topics. Okay, so now I'll start in preparation to studying. You remember that in response to the question of how would you detect that on the lattice, I said that one idea is to put all the spins up on one side of the lattice and all the spins down on the other side of the lattice. And then the lattice constructs a non-trivial interpolating configuration, which you can think of as a domain wall. And this has been seen in the Ising model. So I want to prepare to a similar study in Yangmills theory, to try to understand what would be the properties of this domain wall connecting these two vacua. And in fact, because of the anomaly, this domain wall physics will be extremely non-trivial. And so to prepare for that discussion, I want to to start a small review of ChernSimons theories, and that will hopefully also be useful for Nadi's lectures next week. So now, so I expect that this review will continue up until the next lecture, but today I want to at least start it. So the ChernSimons Lagrangian. We're going to discuss only 2 plus 1 dimensional physics for the next hour or so. So the Lagrangian is given by k over 4 pi a wedge dA plus a mu j mu. So we're going to analyze this system for the next couple of minutes. Let me explain what's written here. Sorry, I'll put a minus sign for conventions. And in addition, k has to be an integer for this theory to make sense. You'll see that many results don't make sense unless k is an integer. So this is called a billion level k, U1 level k ChernSimons theory. A is a dynamical field here. A mu is a dynamical U1 connection. So A is an ordinary U1 gauge field, the same thing that you know from QED. The interaction is like epsilon mu nu rho a mu d rho a nu. That's what this symbol means. And J mu is a classical source. It's a source of J mu is a source of electric and magnetic particles. So J is just a source of some density for charge and some current. And J has to obey the continuity equation for this coupling to make sense. So the continuity equation is that d rho over dt plus di ji equals to 0. That's the conservation equation for J. And this is important for this theory to make sense. Okay, so we're going to try to study what happens to sources in the presence of electromagnetic fields that obey the ChernSimons action. So of course you know a lot about the system when you have F squared here. That's just Maxwell with the sources. You know what happens when electric charges are accelerated or move at a constant velocity or whatever. So here the situation is actually dramatically different. So let's derive the equations of motion. The equations of motion are mu nu rho F nu rho equals J mu. This is the equation of motion that relates the current to the electromagnetic field that responds to the existence of those charges and that may be static or they may be moving. And you can invert this equation and write it as an equation for F mu nu. It's 2 pi over k epsilon mu nu rho J rho. You can just invert this equation. Okay, let's write it in components. So this system is very different from ordinary electromagnetism. And you'll see in what ways this is different. So writing it in components, we see that the density of charge, which is the zeroth component of this J, the density of charge is linearly related to the magnetic field. And similarly, the current of the charged particles is linearly related to the electric field, but in a transverse direction. So if you have some particles moving, this is the magnetic field, and this is the electric field that they induce. So what's the most striking difference between this system and electromagnetism? Does anybody see? What's the most striking difference between this response to charges and electromagnetism? Say again? Exactly. So what does it mean that there are no derivatives? Completely local. It's completely local, right? So the electromagnetic fields here are like slave fields. They don't have their own life. They respond to charges in a direct linear fashion. And there is no radiation. That's one way of saying it. Ordinary charges emit radiation when they accelerate. But here there is no radiation, because the magnetic and electric fields do not emit plane wave solutions. They are just fixed in terms of the charges. So there is no homogeneous solution in some sense. So what is the picture? So if you have the plane, let's say this is the plane, R2. Let's imagine that we have a bunch of charges. So let's take the density, rho x of t, to be just a bunch of particles that are moving somehow. So this is going to be a sum over delta functions. Delta x minus xa t. So, and from this density of charges, of course, you can immediately derive the current. I'm not going to even do that. It's a undergrad exercise. By the continuity equation, you can derive the current of the charged particles. So the picture is that we have a bunch of charges, and I've taken them to be unit charges. This is going to be important. This is a bunch of probe charges that are moving in some prescribed fashion, and they have unit charge under the electromagnetic field A. Is that clear? So we have a bunch of charges, and the reason for this cross is going to be evident soon. So we have a bunch of charges, and they just move in some way. Now, what this cross indicates is that there is a magnetic field that is localized exactly on the charges, as indicated by this, as implied by this equation. So charged particles become slaves for flux. So this cross indicates some flux. So the particle becomes like a little solenoid, which carries a magnetic flux. And this magnetic flux is 2 pi over k, where k is an integer. So it's a fraction of 2 pi. As you remember, 2 pi magnetic flux is a trivial flux. It leads to no interesting consequences, as Dirac has taught us. But this is a fractional flux. So this will have interesting consequences, that these particles are slaves for fractional flux. Now, these charges, if they're static, they lead to no electric fields. But if they start moving, they also lead to some electric fields, according to this formula. So the most interesting thing is that particles become slaves for flux. And in the condensed matter literature, this is called flux attachment. So this is the ChernSimons action is like a natural way to endow electric charges with some magnetic field that sort of emanates from the little charges. Okay. Yeah, emanates is a bad word. The magnetic field in 2 + 1 dimensions is a scalar field in space, just a pseudo-scalar field in space. So the arrows are drawn in a direction that doesn't exist. Yeah. Very good. So this, we can also write a formula. This is a homework exercise. This is an interesting homework exercise for those of you who want to become a little bit more proficient in this business. So you can solve these equations and write the electromagnetic potential associated to a bunch of charges. So there is a convenient gauge where A0 vanishes, and then the answer is given. I want you to show this answer. Okay? Your homework exercise is to demonstrate that this answer is correct. So there is a sum over the particles. Because this theory is linear, the electromagnetic field is just the sum of the contributions of each particle. There are no interactions here, because it's an abelian theory. So we have xj minus xj of t. Well, this is I. Yeah, this is okay. And then there is x vector minus x a vector t squared, and this is x. My a was downstairs. It's becoming a little inconvenient. but once you solve the exercise, it will be clear. Okay, so
Does he have J upstairs in the first term?
because there is an epsilon here,
Okay,
yeah. Now,
no, but okay, yeah.
this gauge field configuration is almost pure gauge, but it's not pure gauge. It leads to localize the magnetic flux at the location of these charges, and there is a very cute way of writing it, which you may want to discover yourself. You can write it as a total derivative of something. Try to see what is the total derivative of. It's a total derivative of something that makes sense everywhere, except at the location of the charges. So try to guess what it's going to be. Okay, so why is this interesting? The reason that this has led to so much activity is because, well, there are systems in nature that are well described by this model. But conceptually, let's take one of those charges and let's compute the holonomy around the charge using that formula, okay? That I haven't proven, but I've given you the formula. So if you compute the holonomy of the gauge field around that guy, you pick up essentially the magnetic flux through that guy by the Ampere or something law, whatever it's called. And that is 2 pi over k. So this turns out to be e to the 2 pi I over k. Okay, this is the holonomy around each of those charges. And this, the way to think about it, about this computation, is that you can think about it as the world line of a charged particle. So this is really the world line of one of those charged particles that we have in the system. And we've just computed the phase that it will pick up when it traverses some closed loop around this particle. So the interpretation of this computation is this is the phase of a probe particle, which is essentially one of those crosses around another cross. So this computes the phase that you pick up when two of those guys go around each other. And you can draw it in space. You can think about it as a process in space, or you can think about it as a question about what happens to the wave function. There is some wave function maybe if you quantize these particles. Or you can just think about it as a process in space where it would be something like that. So you can take two particles, like move them across each other in this fashion so that each comes back to its original position. And you ask, what is the phase that you pick up? This is equivalent to this computation because they just go around each other if you look at this picture. Yes, this is just Aharonov-Bohm. So how do we call particles that have funny statistics? Does anybody know? Anyons, right. So we see that what the ChernSimons action does is to convert ordinary charged particles to anyons. And those anyons are a billion. Those anyons are called a billion anyons because, the underlying dynamics is that of an abelian U1 gauge theory. And you could do like some complicated loops, and it wouldn't matter which particle you wind around first, which second. So everything in the system is kind of commutative. There is some interesting phase, but everything is commutative.
That would be the representation of the wave group, right?
Yeah, I mean you can think about it in those terms. Okay, now another property that I want to emphasize is what is the spin of this anyon. So an anyon, a static anyon, is still invariant under the rotational symmetry, right? If you just have one static anyon in the universe, you still have a U1 symmetry. And the question is, what is the eigenvalue of that U1 symmetry? So that you would call the spin of the anyon. So the spin of the anyon is, of course, closely related to this braiding process, but it's a half of the braiding process. So the spin is essentially, the spin, you can think about the spin as what happens if you take two anyons and you just exchange them. So this is 1 and this is 2. So here what we do is that we exchange the two anyons, but then we exchange them again. So to obtain the spin of the anyons, at least for this abelian theory, all you have to do is to take a half of the Aharonov-Bohm phase, because that would be the phase that you have to add to the wave function when you exchange two particles. So the spin is given by a half of the Aharonov-Bohm phase, which is 1 over 2k. So the Aharonov-Bohm phase is 1 over k, and the spin is 1 over 2k. I'm going to generalize this formula in a second. Is it clear why the spin is interpreted as the phase of the wave function when we exchange two particles? The wave function takes a minus sign if we exchange two spin and a half particles, right? That's Fermi statistics. So this is just a generalization of that. Very good. So here it's not yet clear why in all of those things that I so far said, k does not need to be an integer. You don't see why. Why does k need to be an integer? Seems to make sense even for non-integer k. I mean, this formula would still be correct for non-integer k, and this formula would be correct. So now I just want to generalize a little bit the Aharonov-Bohm phase. Remember that in this exercise that we had here, it was here, we had a bunch of particles which are probe particles. So their motion is not dictated by the physics of the system. Their motion is dictated by an external person that tells them how to move. They are heavy particles and you just drag them in some way. Now, those particles had charge 1 under the electromagnetic field A. And that's why their Wilson line had the coefficient 1 here, because that's the charge of the external particle. However, you can also take the charges of these particles to be arbitrary q, q prime, where q and q prime could be any integers. So q and q prime are arbitrary integers. Then the magnetic flux that emanates through these particles will not be 2 pi over k anymore. It's going to be 2 pi q over k, or 2 pi q prime over k. So it's linear in the charge of the particle. Then you can ask, what is the braiding phase that you get when you move two such particles? Like you take two particles with charges q and q prime, and you do this braiding exercise, which we've done here. So you could take this to have charge q, and this to take to be of charge q prime, and do this braiding exercise. It's a straightforward computation to generalize this thing. You just have to put q here, and remember that the flux is q prime. So this phase is going to be generalized to e to the 2 pi I q prime over k. This is the general braiding phase when you move particles of charge q and q prime across in this braiding motion. From this braiding phase, we see something very interesting that's fundamental and general in ChernSimons theory, which is that particles of charge k seem to be transparent. So you see that as far as the braiding phase goes, if you have an external particle of charge k, let's say, or something 0 mod k, you're not going to be able to detect it by doing Aharonov-Bohm experiments or any other experiments at low energies. So these heavy external particles have some imprint on the infrared only if you can detect them through this Aharonov-Bohm phase. But if they lead to no Aharonov-Bohm phase, there is no way to detect them. So this shows that the number of observables in ChernSimons theories is essentially finite. There are only finitely many anyons, non-trivial anyons. So there are essentially only finitely many non-trivial anyons.
But they seem to have a non-trivial spin.
Right. Now I'm going to discuss the spin for a second. Here we computed the spin, but this computation was a little bit too fast. Because these are external anyons. The idea is that you're not really able to compute the spin of this anyon, because, for instance, this anyon is charged. It's a charged particle. And in the full theory, the gauge field A is not necessarily a frozen degree of freedom. So, okay, let me just explain it a little bit better. In ChernSimons theory, the magnetic field B and the electric field E are both concentrated on these anyons, on these point particles, which are external particles. But in the full theory, if you have good enough resolution, you would see that, in fact, these electric and magnetic fields have some profile, which extends over some small microscopic distance scale, which is not visible to an infrared observer. And in fact, if you do certain processes, you can even emit a massive spin 1 particle. So it's not something that you can do it. If you do a very, very adiabatic, slow process, you're not going to be able to emit a spin 1 particle because they are massive. But that tells you that the spin cannot be really computed. The spin of these anyons is only defined modulo the spin of various massive particles that you don't have control over. So in fact, this spin is defined mod 1. This mod 1 is like saying that in a topological field theory, we're not able to compute the spin precisely. We're only able to compute the spin of these anyons modulo the spin of physical particles in the Hilbert space. The Hilbert space may have like genuine particles which are not anionic, and their spin is going to be a half or 1. So you're always able to glue you can always glue to an anion one such physical particle without changing the AharonovBohm phase. And therefore the spin of the anion is not microscopically, is not inherently well defined. So one way to think about it physically is that you can take an external anion and just glue to it a massive vector, like this guy, or glue to it some other particle. The AharonovBohm phases would not change, but the spin would change by 1. And that's why you're inherently unable to compute the spin. You're only able to compute the spin mod 1. Are there any questions about it? Are there any comments, questions?
Yeah, I think it's imprecise what you said.
I'm just giving an intuition.
Okay.
Yeah, I'm not giving precise arguments. Yeah. Say again.
Regarding Q equals 0 marking transparent, is that true only for integer k?
Is that true only for integer k? Well, you see that for non-integer k, since the charges are the charges have to be integers. If k is a general real parameter.
30 minutes.
Okay, yeah. What I'm trying to say here is that there will be only finitely many observables in the theory, or finitely many non-trivial Wilson lines, only if k is an integer. Because Q has to be an integer, being a charged particle under an AU1 gauge symmetry. Okay, so now I want to get to Subir's question about the spin. So here we argued that particles whose charge is 0 mod k, they correspond to trivial anyons, to anyons with no spin, to anyons with no braiding. But their spin could be sometimes non-trivial. So let's take this formula and try to compute the spin mod 1 of a charge q anion. So the computation of the spin of a charge q anion is follows the same idea, the same intuitive ideas here, that you compute the braiding phase of this particle across itself and then take a half of it, because that corresponds to interchanging the two particles. So the spin comes out to be q squared over 2k. So that's what you get if you just follow your nose, divide the Aharonov-Bohm phase by 2, corresponding to interchanging the two particles. So there is a certain subtlety, there is a certain important subtlety in the subject, which is that even though some anyons could be transparent, their spin may be a half mod 1. So let's take, I'll show you how this works. Let's take k to be even. If k is even, and you plug q equals k, then the spin of q equals k is if k is even, it's k over 2. And this is 0 mod 1, because k is even. But if k is odd, the spin is the spin of the q equals k anion is again k over 2, and this is a half mod 1. So this shows that transparent anyons that don't have any non-trivial Aharonov-Bohm phases, could have either spin 1 or spin a half. And roughly speaking, this corresponds to what's called non-spin TQFT and spin TQFT. So these are often called spin. They might appear in Aristotle, I don't know. Those are called spin topological field theories, and those are called non-spin topological field theories. So the question is essentially whether you have transparent anyons with spin a half. So that's a small technical distinction that's important for various applications. So, okay. Now I want to, I have 10 more minutes. Now what I want to discuss is some questions that are a little bit more advanced, having to do with non-abelian ChernSimons theories. So this is what I wanted to say about the abelian anyons case. Just reviewing the intuitive ideas in this field. And now I want to tell you a few things about the non-abelian case. Are there any questions about the abelian case? Yeah. K is a parameter in the Lagrangian. K is a parameter in the Lagrangian that's physical and measurable. Q is the charge of an external probe particle, like an external enyon. They have nothing to do with each other. And yet, yes?
Yeah, why is it that when we transform the Hamiltonian in the non-abelian case, we end up with a non-abelian ChernSimons factor with only level 1 and not any other level?
You're asking about the similarity transformation? I haven't yet got to the point that I can explain it. I will probably explain it tomorrow when I explain the domain wall construction, and you'll see this emerges in a rather intuitive fashion. Any other questions? Yes?
You said that the reason this didn't apply only mod 1 is because in the actual theory, in the last model, you can emit or absorb a spin on.
Yeah, you can. The anion is an external particle, and it's distinguished by the Aharonov-Bohm phases that you can measure at long distances. So when you can put on top of your anion some physical particle that's non-anionic, that has no Aharonov-Bohm phases, and you would change the spin by 1.
My question was, you mentioned for K odds, you have to have a spin.
Yeah.
Theory would mean that you have to be fundamental fermion. Would that mean the spin is actually only defined mod 1/2?
Right. So if you have a transparent line of spin 1/2, then the theory needs a spin structure to be defined. So, well, you can avoid that by introducing a more sophisticated concept of spin C structure, but let's not discuss that for a second. Let's assume that there is no, in the full Hamiltonian, there is no spin-charge relation, so there is no spin space. So if there is no spin-charge relation in the full Hamiltonian, whatever it might be, then theories with odd K will require a spin structure for their partition functions to make sense and for you to be able to even compute the partition functions. So these are genuine spin theories. Those are like theories with fermions.
Well, I'm just saying that the anion, the same ambiguity that makes the spin only defined mod 1 here,
Yes.
would make it only defined.
Yeah, you could imagine that in a theory with fermions, there is some object that is not anionic, has no Aharonov-Bohm phases, and has spin 1/2. Let's call it a proton. A proton is such an object. So you could just take any anion, put a proton on top of it, and you would change the spin by 1/2. So that shows that the spin cannot be inherently defined, modulo 1 in spin theories of anyons, the spin of anyons. Yeah. Any other questions? Very good. Okay, non-abelian. Just few comments on non-abelian. On non-abelian ChernSimons theories. So one general property of this class of theories that we have so far discussed, they are called, maybe I haven't mentioned the name, but they are often called U1 level K ChernSimons theories. That's the name of the class of models that we discussed so far. So one general property of these models, well, there is this issue of spin versus non-spin for odd and even K. But another general property of these models is that they lead to abelian anyons. So only abelian anyons. Now, for various applications, people are very interested in non-abelian anyons. So the way to obtain theories of non-abelian anyons is to complicate the gauge group, essentially. So one class of models that I want to, I'll discuss briefly SUN level K, and then UN, and then I'll discuss a little bit UN level P, comma Q, and I'll explain what that notation means, what are P and what are Q, and what are their quantization conditions. So let me start from SUN level K. I'll just write a Lagrangian and make a few comments about it, and then I'll do the same for this, and then I'll describe some salient properties of these theories. Yeah. So the Lagrangian for the SUN level K model is given by k over 4 pi trace a wedge dA plus 2I over 3 a cubed. And A is now an SUN gauge field. So SUN connection. Now, so the number of anyons, here there were k a billion anyons. K a billion anyons. Well, k distinct, k, it's kind of subtle to count, but so there were k lines, Wilson lines that were non-transparent, which were labeled by e to the I q a, q ranging from 0 to k minus 1. Those are the lines that have interesting Aharonov-Bohm phases. They are labeled by this integer that goes from 0 to k minus 1. And then the case line may or may not, the case line is always transparent, but it may or may not have spin a half. So you may, so counting them is a different thing. Okay, so for SUN level k, this is the Lagrangian. For general k, by that I mean k is not, that's not equal to 1. And for general k and n, this describes non-abelian anyons. And for this model to make sense, as I said here, k needs to be an integer. This is a complicated, a more complicated system where you, what you do to understand those theories is that now Wilson lines, the analog of this parameter q is the representation of the probe external particle. So you have to specify the representation here. You have to specify the representation of this Wilson line, and then you have to ask yourself, what is the phase that I pick up when I take a particle in representation r, a particle in representation r prime, and braid them. And then you also have to discuss the question of what happens when I fuse two anyons, because it's non-abelian. So these computations have been done in the 80s, and I'm not going to review them. You can look at the papers of Moore, Seiberg, and many others, where this technology is completely spelled out. I'm just for me, I'll just mention some properties of these theories for some special values of k and n that would be interesting for the discussion tomorrow. Now, another class of models are the ChernSimons theories based on the group UN. And they have two parameters, P and Q. Yes? Yes, thank you. So the Lagrangian here, the Lagrangian for this class of ChernSimons theories is given by, so here there is P over 4 pi trace ADA plus 2I over 3A cubed plus Q minus P over N trace of A wedge D trace of A. So this theories have two parameters, P and Q, essentially because there is a different level for the U1 part of the UN group and for the SUN part of the UN group. And those are intuitively P and Q. So you can also think about this class of ChernSimons theories as a product of SUN level P, which we defined here, U1 level QN, and then you have to identify a common Zn factor, because as you remember, to define the group U, we take SUN, U1, multiply them, and identify the center diagonally. So that's the meaning of the symbol here. So this is the other class of theories that will appear soon. Now, what I want to tell you about those theories is that they're not all inequivalent. So there is a bunch of relations between those theories. And those relations are known as level rank duality.
Is it always on the K mod n or K defined mod n?
Yes, so here, sorry, I should have mentioned. Here, it must be true that Q minus P is 0 mod n for this class of theories to make sense. Okay. The reason that this is true is because the integrals of the fluxes of trace A are quantized as the fluxes of any gauge field, And so this has to be an integer, otherwise it won't make sense.
But P on its own does not have to be an integer?
P has to be an integer. And Q minus P has to be 0 mod n. And then this class of theories makes sense. And similarly here, well, here you just have to make sure that the level is an integer. And then this class of theories makes sense. Now, there is a bunch of relations between these theories, which are known as level rank duality. Level rank dualities. Those are interesting dualities because they can be proven. So these are one of those rare cases in quantum field theory where you can prove a duality. Of course, those dualities do not concern with theories that have actual physical propagating degrees of freedom. These are topological field theories that only have some, non-abelian Aharonov-Bohm phases. But it's still interesting that they obey a set of dualities. So there are 3 important dualities that I want to mention, and then tell you one striking consequence of those dualities. And tomorrow we'll discuss more. So I'll just write down the relations. So SUN level K turns out to be equivalent to UK level n minus n, comma, minus n. Okay, so those theories are not all different. There is this relation. And there are actually 2 more relations that I'll actually just need the second one. So I won't flood you with all the possible dualities. I'll just give you one more. So there's K plus n. And this is dual to UK minus n minus k. Those are the two relations that I will need for the sake of these lectures. I would not. There are other relations, and there are many sparse relations, but I won't try to classify them.
Pure gauge theory without any matter field. You can have probe matter and then there's still some mapping. No?
So you're asking about pure gauge theory, pure U1 gauge theory, or?
No, this level rank duality is for this pure ChernSimons without any matter.
Well, the matter is the no dynamical matter.
Okay.
Yeah, no dynamical matter. So in this ChernSimons theory, the observables are external world lines of probe-heavy particles, which have some braiding and fusion. And these arrows mean that those matrices that characterize the braiding and the fusion agree.
But you also need to map the representation.
Exactly. So these dualities are extremely non-trivial. You have to map the representations of the anyons that have interesting braiding phases to other representations here. And there is a concrete spelled out algorithm of how to map those representations. And it's a miracle that everything works. Okay, so the physics of these dualities is essentially mostly about the dynamics of probe particles, but there is a little bit more to it. You can also study these theories in topologically non-trivial spaces, and then you have interesting partition functions, and they also agree. So this is the content of those dualities. Of course, as you know, and I guess Nari will review it, recently people have also tried to add matter fields. Those dualities are then, in most cases, cannot be proven, but those dualities can be proven. Okay, any more questions about those identifications? Okay, so there are 2 striking consequences, one of which is kind of just a technical fact, and the other is really physically striking, and I wanted to give you as a homework exercise to think how could it be. So the first, this is a technical consequence, which is that if you put k equals 1, this simplifies to SUN level 1 being the same as U1 level minus n. What did we say about U1 ChernSimons theories? That there are a billion. So that means that the anyons of SUN level 1 are a billion anyons. So we see that not all the SUN-K ChernSimons theories admit non-abelian anyons. This has a billion anyons only. This is just a technical consequence that's going to be important tomorrow. You'll see what for. The other thing is really striking, and it's obtained by plugging n equals k equals 1 in the second duality. Let's plug n equals k equals 1 in the second duality. What we find is that U1 level 2 is dual to U1 level minus 2. One thing that I want to mention, which I haven't emphasized yet, but this is the time to emphasize it, is that the ChernSimons action is odd under time reversal symmetry because it has an epsilon tensor. Okay? So therefore, time reversal symmetry is not a symmetry of generic ChernSimons theories. So the braiding matrices for these anyons are generally not invariant under time reversal symmetry. Let me write it. It's an important fact. So time reversal symmetry, time reversal is not a symmetry of a generic ChernSimons theory. In general, okay? A general ChernSimons theory will not have any time reversal symmetry because the braiding and fusion matrices are not mapped to themselves under conjugation. However, what time reversal symmetry does is to take the level to minus itself, essentially. So you get a new theory. U1 level 3, if you act on it with time reversal symmetry, you get U1 level minus 3. U1 level minus 3 is a different theory from U1 level 3. So U1 level 3 is not the same as U1 level minus 3. They have different, slightly different Aharonov-Bohm phases that cannot be mapped to each other. The miracle is that for U1 level 2, from this duality, we see that they are the same one and the same theory. So this is an example where the classical Lagrangian is not invariant under time reversal symmetry, but the quantum theory is. So the puzzle that I want you to think about at home is kind of a philosophical question. Usually, we know of symmetries that exist classically, but then the quantum theory ruins those symmetries. That's the ABG anomaly that you asked about. Here, the opposite happens. The classical Lagrangian, to the extent that you can write it down, is not time reversal invariant, but the quantum theory is time reversal invariant. So your homework exercise is to understand how could this be even philosophically, that the quantum theory has more symmetries than a classical symmetry. But more importantly, please compute the Aharonov-Bohm phases in this theory, and compute the Aharonov-Bohm phases in this theory, and check that they agree. Okay, so compute AB phases and check that they are the same in both sides. It's just straightforward, just plug into the formulas that I gave you, and you'll see that the Aharonov-Bohm phases agree. And then just as a sanity check, take this example, plug the Aharonov-Bohm phases, and you see that they don't agree. So it's really a miracle just for level 1. It's a miracle for 2. It doesn't happen for 3, for U1 level 3. Okay, so just make sure that you understand which Aharonov-Bohm phases there exist. There are 3 anyons here, 2 anyons here. So here there is a matrix of Aharonov-Bohm phases, and make sure that it's the same. It's not the same. And here the matrix of Aharonov-Bohm phases happens to be the same on both sides. Okay, so this is the homework exercise, and these things will feature to some extent in what we'll discuss tomorrow. Okay. Any more questions?
First, let's thank you.
Okay. Yeah.
What is the exact relationship between like U1K and U1P?
Your question is what is the relationship between U1 level K and U1P, P comma Q? Yeah. So So the question is what is the relation between U1 level K and U1 level P comma Q? So I gave you this definition that UN level P comma Q is S1 level P times U1 level NQ over Zn. Now, if you plug n equals 1, let's see what happens to that formula. Who asked this question? I forgot. Yeah. So let's plug n equals 1. So what happens to SU1? It's empty. And the index P therefore disappears. And the denominator is likewise trivial. So all that remains is U1 level Q. So there is no U1 theories have only one parameter, which is an integer, not 2 parameters. Any other questions? Okay. So there is. Thanks. Neat.